Welcome to the June 2024 AstroViz Virtual Community Meetup. It has been wonderfully titled Astrophysical Artistry. And today we will have a panel discussion from a team at the Space Telescope Science Institute, followed by a lightning talk from Jack Madden. We will start with the panel discussion, and it is a deep dive into the creation of the pillars of creation. And here are our four members of the team that will be presenting it. Now, I serve as the head of the AstroViz project for NASA's Universal Learning, which is based at STScI. And as you can see from the videos here, we have done the Orion Nebula, the Whirlpool Galaxy, Crab Nebula, Stephan's Quintet, Eta Car, and the Ultra Deep Field in our visualizations. And that's just for the AstroViz project. At STScI, we have done a number of visualizations, and I recently counted, and it was over 70 different visualizations that we have done over my career there. But there is one we really haven't done in detail, and that is the pillars of creation. And Greg Bacon, who's the manager with me of the team, he and I didn't want to do this until we could do it right. We really felt we could do it right. And what enabled it? Well, one, you got this wonderful image from Webb, so we can go back and forth between visible and infrared. And two, we have an incredible team now. We used to have just like 4 of us. Now we have 9 people and a wonderful set of skills, and they will be on display here. Here are the videos they were posted today. If you want to take a screenshot of this, you can get it, or just check your AstroViz Community of Practice emails. I mailed those out this morning. So this is the visualization. For those of you who may not have seen it, I'm just going to go through some screen grabs. And it starts out with a zoom that goes from the scale of the Milky Way galaxy, changes to infrared light to show off other features, continues down to the dust clouds and the Eagle Nebula, goes into the Eagle Nebula, again changing to infrared and X-ray, and then gets down to the stars whose emissions create the pillars. Oh, come on, the pillars of creation here. All right, and so here is the Hubble version. All right, and here is the Webb version. These are actually the 3D models. And so we can fly into them. We fly past that first pillar. We fly up to that second pillar. We fly over to the left pillar. We showcase that jet on there. We come down to a newborn star at the end of there. And then we back off and show you the whole structure of those 3D models within the Eagle Nebula. And of course, the most important screen, the credit screen, the wonderful people who created this, okay? We're going to talk about how we made that today. And I have to start with a disclaimer that all mentions of commercial software are simply factual statements and should not be construed as endorsements. Yes, we've been nabbed for people thinking they could use our comments as endorsements before. All right, so I do the science. Here is the basic science. You've got these ionizing stars. Their winds create the pillars in the Eagle Nebula. How do you do this in 3D? Well, you go to the paper, okay? This is a paper on the pillars of creation where they observed it with the MUSE instrument on the VLT, and they're able to get simple structures and the distances and the orientations and such. And actually this up here in the upper right-hand corner, that's the cartoon model that's in the paper, okay? One thing you need to know is that there are 4 pillars, not 3. It looks like there are 3 in a 2D thing, but there actually are 4 pillars, pillars 1A, 1B, pillar 2, and pillar 3 in the terminology of the paper. And then what you do is you bring in the expert, our subject matter expert, Anna McLeod, who's the first author on this paper. You get her involved in a Zoom call with all of your team, and you go through it. Actually, you do this several times, and you help create this 3-dimensional thing. And for example, you might notice that pillar 3 here is tilted in one direction differently than it was in the paper. So we go through all the science, we set it up, and then we hand it off to the artist to do some more stuff. All right, and so Alyssa, tag team to you. You share your screen, and we will do that. We'll go into your stuff.
Oh yeah, look how fast that was. All right. So I know you're all chomping at the bit to get behind the actual 3D model, but before that, we're going to discuss the zoom sequence very briefly, and that's just sort of a contextual, support to lead up to the viz, act as sort of the context and foundation for the story that we're trying to tell. And so the first thing is we have to consider plates, alignment, transitions, and timing. So plates are just all the images you need to get to point A to point B. So your starting image, wide field image of the Milky Way to a Hubble or Webb image. And then you have to think about aligning all of these images together. And you will want to eventually combine them in such a way, either in sort of like a comp form, like in After Effects or parenting, in order to have them scale uniformly. So that's how you get your zoom. And then transitions will be important for various reasons, but the main transition we're talking about is from plate to plate. So you have the illusion of endless enhancement, endless resolution, and we have to think about the timing. So in general with zooms, we use exponential zoom. And that is just a way to make sure that the zoom is consistent speed throughout, or else if you use a linear zoom, then you would start off very, very fast and end up very, very slow. So we don't want to do that. But for this particular viz or particular zoom, we have story to tell. And so there's regions where we want to sort of linger on. So we have to also invoke time remapping. So we'll talk about that very briefly. Okay, first the plates. These are all the plates that are in the zoom that you might see or might not see. But there's a total of 11 plates. 6 of them are critical to sort of maintaining the resolution throughout. And then the other 4 that you see here are the multi-wavelength images that we care about for the story. So we have the infrared up here, we have the Spitzer and the X-ray. And so finding plates can just be a little bit tedious just so that you can find the right field of view that you want. But you just have to search for them in sort of any outreach archive. So a lot of these are from ESO or they're from some sort of free stock, footage stock, whether it's Wiki Commons or I forgot what this one was. Adobe, yes, Adobe stock. All right, so alignment. This is pretty straightforward. We have to have all of these plates aligned with each other. It gets a little bit more complicated though when you have such a difference between these scales. So you have like a very wide field image and then sort of a narrow field image. So there can be geometric distortions between observatories. And so that's the case between this ESO image and the underlying image, which is the Milky Way. All sky image here. And so I use a mesh warp. Actually, let me go back. I just use a mesh warp in After Effects. I find that that's the easiest thing to do. Generally, you just need to use sort of scale and rotation adjustments. But you can see that makes a big difference. And if we kept it without making those adjustments to the warp, then we would have sort of the image you see first, which is very, distracting. And then next transition. So there's a couple of different transitions. And then specifically, I'm going to talk about the transitions between the plates. You want to blend them in together again to make it seem like a seamless zoom. The first thing you got to do is that the plate on top, you want it to blend with the plate underneath. So you want to create a mask. You can apply a mask in After Effects. You can feather and you can expand that mask inward in order to blend it to the bottom plate. And that's what I do here with this Darko image. And you can see also you have to apply a lot of different effects, curves, adjustments, etc., in order to blend, again, this top plate with the bottom plate. You're applying all of these effects, though, to your bottom plate. You always want to kind of work up in that way, or else you're going to have to like start changing things all over. So that's one of the transitions. There's also transitions between different parts of the spectrum, which you see in the zoom. That's just we just want to make it clear that we are shifting to a different part of the spectrum. And then there's the last transition, which is the big transition, using these expanding circles masked over the Darko image to reveal the 3D model. And so it's important to ease this transition because there is going to be a little bit difference between the ground-based observations and the model itself. And then lastly is the timing. So again, we start with an exponential zoom, which you can sort of see here. And they are in After Effects, there's functionality to just create these keyframes, bake them in to create this graph you see here, the Bezier graph of the keyframes. I also delete some of the keyframes in the front and the back just because, or not the back, the front and the, well, yeah, no, front and back, beginning and end. just to ease that sort of transition at the end, because if you just use it straight up, it's kind of harsh. So that's what I do there. And that's the first thing we do, but we can see that it's quite long. It's over 2 minutes. So we want to cut it down a little bit. And we also want to focus on the specific parts of the story that we're trying to tell. So that's where time remapping comes in. So we take that exponential zoom and we have shortened it to less than 2 minutes. That's great. But you can see where there's transitions happening here. In the beginning, we are cycling through the multi-wavelength images of the Milky Way, the all skies. So that's slower. And then as we're pushing to the pillars, that gets faster. And again, we slow down so that we can also appreciate the Spitzer and the X-ray. So that's what I have there. And that will transition into the 3D model. So I'll hand it over to Leah now.
All right, thanks. Let me... All right, yeah, so hi, Leah Hustak. As Frank mentioned, I'm a senior motion designer, so I'll be walking you guys through the modeling and texturing process portion of the viz, and then later the compositing process after Ralf handles the phagometric work. I'm mostly going to be showing the process for Hubble for the sake of time, but the Webb models went through a similar process. The main difference between the Hubble and Webb models is that the Webb ones are slightly smaller than the Hubble. And they're slightly inset. The textures are the main difference though, as well as some of the compositing, just because the Webb one needed a little more transparency work. So for making pillars, like, where do you start? There's a lot of ways that you could do it, but I decided to start with just basic boxes. I used a combination of texture projection and 3D lighting based on the physical star locations to influence the sculpting in Maya. The lighting was used kind of as a guide to match the gold tones from the Hubble image, which are the areas that are lit by the stars. So you can kind of figure out what areas are getting the most light versus less to help you figure out where pieces of it are positioned. I'll get into the lighting aspect in a second, but there were a lot of iterations of the models and different placements after discussions with the team and Anna. The basic process was laying out the boxes, merging them together, soft sculpting until the basic shape was established. Everyone agreed on it, and then we moved into detailed sculpting. So the 3D lights in the scene were placed based on their location in the kind of extended image, as well as their rough location, rough known location in relation to the pillars. And we used the lighting to kind of rough out the shape of the pillars and then refine from there. In the end, we ended up using 2 main stars to influence the lighting of the model. And you can see in here the front and side view. Basically, the distance between P1A, P2, and P3 were equal, and then P1B kind of set in between P1A and P2. And this is the final lit view of the high-resolution sculpted model in relation to the star placement to give you a better idea of the lighting. And this is a comparison between the final lit model and the gold tones from the Hubble image, showing how the lit areas kind of influence the shape. It's not a perfect match, but it's close enough to be reasonable for the visualization. The streaming bits that come down from P3 aren't shown just because they were flat or barely sculpted planes that were kind of later in the process and weren't like a major concern during the main sculpting. But since this is a full 3D model, especially for P1A, there was some other stuff to figure out, which included the back of P1A. This took a bit of thought, but after talking to Robert about how to use the infrared views of the pullback sequence seen at the end of the visualization, and how to use the infrared to kind of inform the layer placement, we've kind of found a crafty way to use that to help. Since you can see through the like dense dusty regions using infrared, the very bright regions of the Webb image is actually where the energy from the stars are interacting with the nebula on the back. So we use the Hubble image to sculpt the front of P1A and then use the bright yellow areas from the Webb image to sculpt the back. And these are the final models for the Hubble full set. The bases for everyone but P3 didn't matter too much since they're mostly transparent or not seen in the final visualization sequence. So those can kind of just be vague shapes. But the issue we ran into that I should have thought more about in the beginning was since the camera's going to be going off axis when you look at P1A up close for Hubble, and also Webb, we did both. You couldn't just use straight up plain texture projection, which we relied on for the other pillars. You actually had to go through the UV mapping process and repaint, which turned into being a painful process. So learn from my mistakes on this. And UV unwrapping is the actual worst, and personal opinion on that. So my original bullying boxes together and then sculpting modeling came to bite me later in the process. Since we're going off axis a lot, the projection wasn't going to work. I made this mistake of assuming I could just bring it into Mudbox or ZBrush and just paint it, export it, hand it off to Ralf and kind of call it a day. That was not what happened. And the ones that I made were bad and had to be fixed. UV mapping is something I've always struggled with, so wasn't great. And whatever ended up being the process to fix it was pretty painful. I ended up having to use the most roundabout way possible, which was using a combination of Houdini for poly reduction of the models, then moving to Maya for projection baking, ZBrush for UV unwrapping, and then Substance, Adobe Substance for actually painting the model. Also, ZBrush's UI is painful, and I hope someone else agrees with me if they've used it. And then this is the last thing I'll share before handing it off to Ralf, but this is an example of the areas that were painted for correction. There's still some texture stretching that was seen, but we weren't going off axis that far. And the other ones, P1B, P2, P3, weren't going far off axis, so we didn't really need to paint those. Once the texture was for P1A was painted, I was able to hand it off for volumetric work, and that's where I'll let Ralf pick up.
All right. Hang on. Let's go, everyone. Let me share my screen real quick. Screen 2. Yes. Okay. Can everyone see it okay? Zoom shifted things around. Okay,
Yep.
Great. Yes, yes, my name's Ralf. I'm a 3D artist, and I worked on the volumetric look of the Pillars of Creation, because not only did we model all of this, we also rendered it in full 3D with volumetric smoke-like effects. And volumes, as some might already know, it presents a whole host of new challenges and problems that you might not get otherwise with just plain geometry. So some of those challenges involve generating the volume from the 3D model with a variation in density, so it's not just a perfect same density throughout, applying a 2D texture to a 3D volume, we'll get into that in a bit, and then creating volumetric ion wind, and putting all these into multiple render passes, which Leah will talk about more in a bit. So to solve most of these problems, we opted for using a program called Houdini. This is a node-based program, and I'm sure if there's any Blender users here might already know how that workflow works, but essentially each one of these nodes, and this is the actual node tree that was used for the pillars, but each node is essentially a set of instructions that the computer does to everything that propagates through it. So here at the top we have pillar 1, and then it feeds through all this huge node graph, and then out of the bottom you end up with a final volumetric pillar. And part of what made Houdini very useful in this process was that this node tree is reusable. So once all the heavy lifting is done, all the hard work is done up front. It basically comes down to feeding a new pillar into the top, and then just making small tweaks throughout the node tree, and then your next pillars are good to go, which is really useful considering we had 4 pillars for Hubble, 4 pillars for Webb, total of 8 pillars. Would have been a lot of work to try to do each one of those from scratch. And of course, also Houdini does have a very robust tool set for dealing with volumetric effects. And so generating the volumes, and this screen grab, I have all the pillars all together, but this tree was applied for each pillar individually, was basically just inputting the 3D geometry that Leah sculpted, and then converting that into a voxel grid 3D, with basically just a bunch of 3-dimensional cubes that define density. And then there's also some fractal noise within this density. A little hard to tell on this screen to capture, but there's some fractal noise to kind of give some variation in the density. So as the camera moves around, you can kind of feel a little bit of parallax in depth. There's also a way to hand paint some density, which was especially helpful in web, where it's a much thinner, the gas is much thinner optically, and so we needed to have some parts of it that were specifically thin that couldn't just be handled with fractal noise. And then from there, this is an exaggerated view of what was actually done. We distorted the density so that it had little plumes and wisps and things like that, so that as the camera got closer, you could see some additional volumetric detail that you might expect as you were to get closer to something like this. Again, this is more than what was done in the final version, but that's just so you can see what was actually done. The density was relatively easy as far as this whole process goes. That's mostly just fill a model with voxels and define a density. A few other steps, of course, but the real challenge was dealing with color projection. So we couldn't recreate the colors from scratch because that would have taken far too long and probably would not have been exactly what we expect to see from the imagery. So we used the telescope imagery to project onto the volume as you might with geometry. And as Leah showed earlier, orthographic projection on the geometry can have some stretching. And it turns out that with volumes, that stretching is even worse because as you rotate to the side, you have what looks like essentially a projector projecting through smoke. And this ended up being a lot less forgiving as far as the camera angle. I mean, if the camera moved just a little bit, you could tell where the issues were. And so this only works from the perspective of the projector. So to solve that, so I've got the model here, and if you look closely, this isn't the model. This is a points scattered across the surface of the model, roughly 80 million for this particular pillar. And each one of those points is sourcing the color of the pillar from the UV texture that Leah put together, that she went in and painted in Substance. So that's why we're not getting some of the extra stretching that she was showing on an earlier slide. But the problem from here still was that when this was converted into a volume, it still had that projector through smoke look. And so to fix that was, the main issue was as you're seeing through this thing that's a volume that has depth, all those really fine, crispy details were still creating little streaks through the volume. And to fix that, I took the points that were on the surface and then created a dense grid that filled the interior of the model, and then transferred the color of the points on the surface to the dense grid on the interior, and then set up a node network that would actually blur the color attribute from the surface the further down you got into the volume. So the colors were still accurate, but the deeper portions of the volume became more diffused, and that gave us the volumetric ethereal feel we were looking for, while solving the problem of the volume leaving very fine and detailed streaks from the texture projection. So moving on from there, another issue we had to figure out was the ion wind, which was from where the stars are, the starlight's hitting the back of the pillars and causing ionization. Our initial tests involved particle simulations, which is another thing that Houdini's pretty good at handling. And the results visually looked pretty good, but the main issue was that changes were really slow and difficult to predict. Simulations are really fun and cool and interesting, but when we're dealing with things that have such explicit and essential details that cannot be just guessed on, we needed much more fine artistic control. And we couldn't, if we decided, well, this is, some of the haze here is too long or stretches out too far, we couldn't take the time to adjust the input velocities and hit a button, wait 10 minutes and see what we get and hope that it was what we wanted. And so this was not a viable solution. And so how we ended up solving that was actually another artist on our team, Joe Olmsted, who he's not on the call today, but he came up with this idea of using Houdini's hair grooming system, where you could have very precise control over where you would grow hair. You could cut it, you can grow it, you can deform it and shape it, all in relatively real time, so very quick and easy artistic control. And then once you have all those splines coming off the pillar, wherever you can put a point, you can make a volume. And so from there, we ended up with converting that over to volume. So it was artistically looked much more along the lines of what we wanted, and also was very easy to adjust. So we could look at it and go, oh, well, this part's too long. You just cut it like with a pair of scissors almost. It just made it much simpler, much faster to iterate. Iteration is very important to the artistic process. You have to fail at things quickly so that you can get to where you want to be. And so we actually like that solution so much. We use it in a few other places in the pillars. So like in this example, we use the same method to generate just this little haze to surround the pillars. We saw a lot, especially on pillar 3 towards the top, had a really nice haze around it. And we thought, well, that hair thing worked really well on the other stuff. Let's use it in other parts. So that ended up enhancing parts of the project we didn't even expect. And then all of this, we ended up rendering in many different passes. So this is the render node tree that we have set up in Houdini. And we rendered approximately 5 separate nodes per pillar. You can see each one of these nodes is a whole render of the whole animation of a portion of the pillar. So that would be like the base volume, have fuzzy details, ion wind, things like that, all these different passes that we would then bring into Nuke. And also each one of these nodes has 3 what we call multipass renders. So there's the beauty pass, which is the just the whole thing all together, exactly how you expect to get out of the render. Then there's the emissive color, which is just like the volume and the color with no lighting. And then there was actually a light in the Houdini scene to backlight the pillars. And the reason we're doing this multipass rendering, and Leah's definitely going to touch on this after I'm done here, is essentially, so for example, the light. If as the camera moves around and let's say the backlighting is too bright, we don't want to have to re-render that whole thing. So having that as a separate pass and compositing helps to have more control over that without having to spend more render resources. And also, just side note, with all these different passes, we totaled over 300,000 frames that were rendered out of Houdini at 60 frames per second. So this was a very big render project. And with that, I think Leah can take over from here.
Cool. Yeah, so I'll walk you through the compositing process. So basically everything that Ralf rendered out came to me along with, I rendered out my own geometry passes of everything, background plates, all that kind of stuff. So I'm gonna go take you through compositing and maybe touch on the 2.5D 3D combination pullback if I have time to do that.
We're running a little long, so.
Okay, yeah, I'll skip it then. All right, yeah. So for each base volume render that for each pillar, there are 4 passes that I got that I used RGB, alpha, combined emission, combined volume. Not each pass was used for the composite process, but they're all considered. So 8 pillars with the base volume passes, each with 4 passes. And then along with the base pillar, there were the long hair, short hair, ion wind, geometry renders for both Hubble and Webb, then single gas cloud pass jet renders, and all those combined together to form kind of this huge like pass group. And this one is for Hubble. There was also one for Webb. And also, yeah, there was backgrounds for both of these. All of these had to be organized and then layered for the final visualization. For that, I used a compositing software called Nuke by Foundry, which is node-based, kind of similar workflow-wise as Houdini, as in that it's kind of like a tree that flows down. So basically anything further up is kind of the background, and anything further down on the node tree stream is closest to the viewer. I maybe could have used After Effects, but Nuke is basically a compositing powerhouse, and I trusted it more to handle the amount of frames and effects we were going to be using in this whole thing. I think Frank calculated it was 1.5 terabytes of layer frames that went into the composite. So we needed basically as much of a secure software as we could use. The Hubble composite ended up being a total of 31 render passes combined. And basically my technique was to divide the sections into individual pillars and then handle the looks in those and then combine them together in the larger stream. I also did this with the web pass, which was similar to the Hubble one, but it used 27 passes instead of 31. Just that's how it ended up. And the setup was slightly different for P1A due to the amount of transparency needed to get the look and feel. This is a close-up of the network used for Hubble's Pillar 3. There was a lot of like roto work, color grading, glows, blurs, channel swapping used in the composite of the whole piece to really control what areas were soft and more volumetric versus the areas that needed a bit more of a harder edge, which would have been like for the geometric pass. This was a lot of organization to keep together, and staying organized was like very, very important for the compositing process. And then once all of the compositing was wrapped up for the main sequence of the visualization, it was then integrated with the 2.5D pullback sequence, which is what's at the end of the actual video, where you start close up on a star, kind of on the finger of P1A for the web version, and then pull all the way back to the Darko image of the Eagle Nebula. And that's kind of what I have on this section. I don't know if we have any extra time to handle the...
We're out of time.
All right. Well, I have a whole thing
We've
on
almost hit 30
2.5D.
minutes here
It's
now.
different time. Okay.
Okay. Why don't you stop your screen share and I will put up a background image for us to take some questions from folks. Okay, so folks, if you have questions, put them up in the chat, and we will try. Actually, you know what? If I share my screen, Robert, I can't see the chat. So somebody else will have to take.
All right, I'll keep an eye on the chat for you.
Oh, no, I figured out a way to do it. Okay, go ahead. Question for Leah. As an amateur modeler myself, when I'm UV unwrapping, sometimes I end up having to go in and adjust literally vertex by vertex. And I always think there has to be a better way. However, with you as an established professional saying that UV unwrapping is the worst, can I rest assured that I'm not missing some sort of magic wand for UV unwrapping? Sometimes it's just that tedious.
It's the actual worst. It's always that tedious, and there's a reason why people like that's their whole career is they get really good at it and do it forever. I used ZBrush particularly because there's a thing you can do in it where you paint where you want the UV, like where you want your seam to be, which was the easiest way for me to be like, there's so many polygons in this model. I'm not going to hand unwrap this. I can just paint the areas where I don't want the seam and then paint the area where I want the seam and unwrap it. And that was the easiest way that I found. There is no easy way to UV unwrap. I wish there was. I'm hoping that's like one of the few things AI might be good at.
Robert, do we have any raised hands? All right, so I have a question
No.
I have a question for Ralf. Ralf, you were a brand new member of the team last fall. Matter of fact, we started this project before you joined the team. You've only been doing commercial stuff in advance. What is the difference between doing commercial stuff versus doing a science-based thing?
I'd say that the biggest difference is the importance of accuracy. Oftentimes when dealing with commercials or visual effects or anything like that, there's a lot more room for artistic and creative control. Not that there wasn't any artistic and creative control on this project, but there's a lot more wiggle room to just kind of do whatever. I mean, even talking about the ion wind stuff was like, in the commercial world, you could just throw up a particle sim and say it looks good, and then or it looks really cool and be done. But this was like, well, it looks cool, but it doesn't look right, and that's the problem. So
Yeah, we didn't, it was particularly on pillar 2, right? We just
Yeah.
couldn't get that looking right. And it was like, I wanted you to clip the hair and it just didn't work.
Yeah, and it was like, oh, we need that one portion to be shorter, and then it's like, then you got to like wait 10 minutes to see the simulation, and it's like, well, that doesn't look, yeah. So I'd say the necessity for being accurate is much higher in the scientific world, which I like. But
Jack, you
it
have
is
your hand raised. Turn on,
Yeah.
unmute yourself and ask a question.
Yeah, I'm curious what the reaction was from the scientists as you worked with them through this and giving them the final product.
All right, so this is one of the reasons why I always have a subject matter expert on the team, so that I can go through an astronomer and say, here's what we're doing, and what do you think about it? And I try to make sure they understand that our goal is not to be scientifically accurate, but just scientifically reasonable, because no one knows the exact structures here, okay? The exact 3D, I mean, you've got one of the world's experts on the pillars of creation on the team, and she can't tell us yes or no about certain things, right? So as long as I don't do something that your average astronomer looks at and goes, whoa, no, as happens so much time in watching sci-fi movies, right? And I have shown it to a bunch of astronomers here at STScI, and they've all enjoyed it. And in particular, they enjoyed it with the narration, where we're actually talking about and discussing things, because they like it that it's providing the scientific context and the scientific knowledge along with it. There is a version of this that's just the music and the fly-through, which is what the missions wanted. Matter of fact, NASA is promoting that one today. But they actually, surprisingly, astronomers enjoyed the narrated one more. Question, AJ, you all mentioned Maya, Houdini, After Effects, Nuke, and more software. How do you choose which software to use for what task, and do you struggle with moving data between them? Yes, AJ, there's always a struggle putting things between things. I grew up, the only thing I know how to use is Maya and After Effects and a little bit of Houdini now, because the team and so Greg and I, as the ones who helped, who get to say, yes, we can use that software, very cautiously move to new software, because we don't want our team going off in too many directions. Like Ralf came in knowing Cinema 4D, and we said, no, we're not doing that. We got enough tools. In terms of the data back and forth, Leah or Ralf, you wanted to comment on getting things back and forth?
I mean, it wasn't too bad. Also, Ralph and I literally sit next to each other, so I can be like, hey, do you want an FBX or an OBJ? It's fine. I'd say we have like a central file sharing thing that we use that makes things quite a bit easier, so we can just grab each other's files from there. And as far as picking a software, it's kind of a, hey, this doesn't work, what else can I use kind of thing. Especially for Houdini or Nuke, it's a, how quickly can I replace this file and then get the same or similar scaffolding of results. Specifically, ZBrush was a last-ditch effort to get UV unwrapping to work, and then Substance was a please let this work for painting kind of move. Those were last-ditch efforts. So
Okay.
keep going.
Robert's pushing me to finish up. We get one more question. James, you have a raised hand. You can ask the last question.
Hey, thanks. Awesome. Beautiful work. Just wondering how, like, so when I think it's around like minute 2 in the video, when it starts to zoom back, you see other objects sort of moving relative to each other as the camera changes. How large is the whole 3D model of this? Is it just the pillars and the other gas things are like flat, or is there more to the 3D world?
Okay, so that very last sequence, what I didn't give Leah time to talk about because we were going too long, is actually the 3D model of the pillars, and only the pillars are 3D, and everything else is 2.5D. They're flat planes placed in 3D in Maya. So we took the Houdini render and we dropped it into the Maya 2.5D, and then rendered the stars and stuff, and moved it all together.
I can throw a screen grab of it into the chat.
Okay, she'll throw a screen grab into the chat.
Awesome. Thank you.
All right. Thank you for all your questions. But now we are going to go to Jack and his lightning talk, and I'm going to stop my share.
Thank you. Man, how do I follow that up? I'll try. You guys should all start putting like cosmic hairdresser on your job titles. It's really great.
Well, if you want to joke, I immediately thought, oh yeah, those 4 pillars, they're a barbershop quartet.
There you go. All right, thank you all for having me. So I'm Jack Madden. I'm going to be talking about a course I taught at Rhode Island School of Design called Astrophysics for Artists. So just a little background on myself before we get started. I got my PhD studying the habitability of planets, and also did a fun side project on the effectiveness of virtual reality in education. I've done a lot of design work during my PhD in data viz and journal covers, teaching workshops on scientific design. And then after my PhD, I actually went to art school. I went to RISD to get my M.F.A. To do more emotive data and conceptual art in their digital media program. And then that's where I started working and then teaching this course, but now I'm in Pasadena. So astrophysics for artists. The first goal of a course like that is to teach some basic astronomy literacy to artists, which in itself is a novel idea, but it was easy enough to do. I've taught intro astronomy before. That wasn't the challenge. The challenge for me, though, was to contextualize astronomy as an artistic endeavor with a room full of other artists. So I had to kind of feel around and get a sense of where the veil between these two worlds is the thinnest and use those as doorways. You don't need astronomy to draw a galaxy or to render a planet. You don't need that physics knowledge. But what I was trying to do was introduce the students to the science in a way where they could get comfortable playing around with the ideas. I didn't want to kind of stand in that doorway to astronomy and just hand them the knowledge that I thought they should know. I kind of wanted to invite them in. So this is how I structured the course. We bounced between the science and then discourse, and then lots of meanders on both sides. And we started with, where you always start, just kind of a basic overview of our place in the universe. So for an example of how this was structured, when you start that first lesson of where we are in space, you might show the powers of 10 video. And what you traditionally do is you show the video, you explain the structure of the universe, how all the different features evolve over time. But since it was a group of artists, we also spent time talking about the actual design of the video and Charles and Ray Eames and their design studio and how they thought about creating such an iconic piece of science visualization. Another example would be on our lesson about light. We learned about thermal emission and absorption spectrum and how you can use that to find elements out in space. But that helped us understand some of Olafur Eliasson's work and his Room for One Color, which uses sodium vapor lamps to create this kind of surreal space where there's no color and how people interact differently when there's not any color. So we kind of had both of those going on. And it was like this kind of, these kinds of conversations that allowed us to break apart this barrier between the art and the science. We would be doing a demo and it would become apparent to the students that these demos could be shifted more into science or more into art, depending on how you framed it. We went on to talk about all different other topics, black holes and search for life, relativity as well. So when we got to search for life, it allowed us to kind of talk about not only the science, but also the way that the search is influenced by art and media. I was able to share some of my own experiences firsthand, trying to translate single data points in my own work into photorealistic visualizations and kind of the pros and cons of that type of approach. Search for life is very theory-laden at the moment, so it's very sensitive to kind of scientists' cultural differences and media consumption and different camps of thought, which can all be swayed by art. Here's another example of kind of the situation right now. Our creative technology has far outpaced what what science can deliver to us. We can make these photorealistic representations of phenomena that we've haven't observed yet. So it's this really uncanny place to be in visualization. It's kind of this, it can be seen as like a breeding ground for bias, and we have to tread carefully as creatives and scientists to like be aware of our responsibilities in creating the images that we do when it could be generations before we actually can ground truth what we're showing. We went through black holes as well, kind of fit into that same venue, looked at the history of some of those representations and the influences there. We also looked at just all different kinds of biases in the way that we look at things and how scientists use data and either succeed or fail at using design principles in their data representations. Things like Askham's quartet and Edward Tufte's work in visual perception. We even got into some art history and the relation between romantic landscape painting and Hubble and now web images from Elizabeth Kessler's work. Just kind of showing that whenever there's humans involved, even if you're working with raw data, there can be, you can carry with you some unexpected values. And one of the final examples I'll show is the traditional ways of visualizing space images are very steeped in the scientific analysis. The first thing you do is you stretch the data, pull out as much contrast and structure and distinction as possible using color. And it does have somewhat of an extractive tone, so I taught some of the students how to process FITS files on their own and was really surprised how much they diverged from that traditional view when they got to see the subjectivity involved there. So I wanted to show a few resources from that course. Hopefully you guys can see the screen here. Yeah, you guys can see the screen there. So I'll put these links in the chat, but I'll send you the whole syllabus for the course. And also this set of resources that we put together that just kind of compile, like if you think of what the art medium is, if you're interested in astronomy, like the medium that you're going to be crafting your work in is all of these data sets and databases of pulsar catalogs and gravitational wave catalogs, image databases. Like this is where you're getting your raw material as an artist if you're working in astronomy. So we put these all together with the artist in mind, and so I'll share this. It's not complete. I'm looking for more additions, so if you have any more, please send them to me. Digital assets, Universal Learning's there. All you guys are there, as a part of this endeavor. And there's also lists of artists and scholars working in art science and astronomy. So let me see if I can find the chat and paste those links in. But yeah, I'll take some questions.
That's wonderful, Jack. That's quite an impressive list of resources that you've assembled. I mean, I was watching you go through them, and I was like, I knew half of them.
Yes.
And I'm like, wow, this is really
Oh yeah,
great.
it's really surprising.
All right, do we have questions for Jack? Or Robert, did you want to go directly to the breakout rooms?
Actually, I'll ask Jack one question myself here. And that's having the chance to sort of provide the science instruction in the context of art for the artist. Did you see like a spread in reactions of the artists to that? Like, are there some who got really interested in the formalism of the science, or was it more like, oh, this is kind of resources I can mine to do more creative things? Because obviously there's such a spectrum with, astronomy illustration on one side and then purely conceptual art on the other. Did this approach of teaching the science, did some of them get kind of interested in the science formalism as part of that?
Yeah, there's kind of a range. I think part of what I wanted to do by showing let's calculate a wavelength transition and talk about olefin lines. Let's do both. it kind of demystified some of the astronomy. Like it kind of disenchanted it a little bit, enough to make them feel comfortable working with it, which I thought was really interesting and what I had kind of hoped for. Right? Like to an outsider, having no education in astronomy, it can be quite a romantic field, and to kind of give them that step inside, and even just the confidence to do it was really fascinating to watch. So we got a range because they were all from all different departments. They had all different mediums of their own and practices of their own. I did prepare so it was a studio course, so they actually had to make something by the end. And I have some examples of that if anyone wants to see.
Well, what I like about it is that we do this so often, and our visualizations are meant to excite them, to get them to want to know more. And here you're combining both that and the teaching as well. We have a question from Tasneem.
Yes. Hello, can you guys hear me?
Yes, we can hear you.
Yeah.
Hi. Well, thanks for the presentation, Jack. I have an astrophysics degree and I'm also an artist. I was just really interested in what kind of other mediums did the artists that you taught use? Was it all purely just data, or what kind of other projects did they have by the end of the course?
That's a great question. I'm trying to see if I can bring up some. So we had, let me just show briefly some of their work. Let's try to sign off for that one. So one of the students hand animated a visualization from Greg Bacon, kind of imbuing it with some more of that emotive feeling when they're reading descriptions that are all anthropomorphized. These are talked about as siblings or companions. This is eventually the homunculus nebula. So they kind of personified a lot of that animation. Created this really beautiful 30-second clip. I had one student kind of learn JavaScript to kind of interact with their feelings about how weird special relativity is, and they would be doing paintings and then overlay animations of these clocks moving at different speeds. I had one student kind of try to capture like the eeriness of Voyager, and they used these audio clips from the plasma wave system to kind of play into this poster series. So they kind of embedded some of those in there. So there was a whole range. One student did a whole virtual reality thing. This was more like education focused. So they did a whole virtual reality space that looked at star evolution. Someone also like knitted a garment that was about like red shifts and blue shifts from black holes, like space-time. So we had the whole range.
Excellent. Yeah, you had a question that people wanted to see the examples of the projects.
Yeah. Yeah, I have a few more if we want to look at them in the breakout.
So Jeff Nee asks or comments at least, even at NASA, I hear the myth of left, right brain, creative scientific thinking a lot. Was that prevalent in your students as well? If so, how did you tackle the challenge of breaking down barriers, exploring that scientists can be creative and artists can be analytical?
Yeah, it's a great question. So it's like the first thing we have to break down is that there is a distinction. And one of the ways I describe it, if I'm doing it quickly, is that an equation, if you look at an equation, like the equation isn't science, right? Like you can say it's part of the science, but it isn't the science. The same way you might look at a painting. The painting itself isn't art, just the same as the equation isn't science. The art and science are both processes. They are both ways of understanding and thinking. They just have to deal with different mediums. They have different outcomes. They're different goals, but they're both processes. They're creative processes. And you can use creative processes in all different ways. And you can take some of the experiences in that art process, use them in scientific processes to get a better understanding, or vice versa. So it's just kind of being open to this idea that they're both process-based endeavors and are very versatile when you have that mindset.
Okay, we had a hand up from Dean. Dean, you want to ask your question?
Sure. Are you able to hear me?
Yes, we can.
Yeah.
Okay, wonderful. Thank you for your talk. And I study both physics and art, and I find it very inspiring. I find in my work it's common that I like go so deep into the astrophysics that I almost spiral out of the human, like the humanity aspect of what art is about. How do you find the humanity in your artwork? I guess is my question for you.
That's a good question. A lot of my own practice is about doing that, like exactly that, and just experimenting with trying to find it. I don't think any of my art like provides answers that way. It's all attempts, just the way science is like this too. We're always experimenting. We're always trying something new, seeing if it works out. Like it feels the same in art. So I do a lot of that, where I take a scientific idea that I had and see if I can kind of make manifest the way I feel about that information. Like this idea that we won't have an image of a habitable exoplanet for maybe the rest of my lifetime, but I have all of these images of places that look really interesting from science fiction. Like how do I reconcile that? How do I deal with that? It's kind of this funny inflection point. So I kind of make work to explore that idea.
All right, we are coming up on an hour, so we're going to have to end the formal part of the session here. I see there are at least one more question or two more questions in the chat. If you would like to chat informally or ask more questions, we can stay on and do that. But we're going to have to wrap up our recording. So thank you, everyone. Thank you to Jack. Thank you to Alyssa. Thank you to Leah. Thank you to Ralf for joining us today. And we do hope you will come and join us again in the future.